Okay, hey, welcome back. This is now 9.7, and we're going to start connecting functions to polynomials. Recall, ultimately, our goal here is to show that you can take sequences of polynomials and kind of show that if you take the limit of those polynomials, that they converge to functions. Okay, so for instance, if you have, let me write this, S1 equals X, S2 equals X minus the polynomial X minus X cubed all over 3 factorial. S3 is the polynomial X minus X cubed over 3 factorial plus X to the 5th over 5 factorial, on and on and on. If you take the limit of the S sub n thingamajig, that's actually going to converge to, in this case, it'll converge to sine of x. Okay, so we need to kind of figure out how the heck to make these polynomials, and that's kind of what this section's about. These last three sections have always been kind of awkward to teach, I think. They kind of jump around a little bit, so please just bear with me and remind yourself, the ultimate goal for us is to kind of show this fact that ultimately we can kind of even replace sine of x with this infinitely long series. Okay, so x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. This is kind of our goal, and that'll allow us to figure out things like, what is the sine of 1? Right, sine of 1 is 1 minus 1 cubed over 3 factorial plus 1 to the 5th over 5 factorial minus 1 to the 7th over 7 factorial plus dot dot dot. And then this thing, is just the regular series that we've been looking at. The big difference here is that this thing is what they'll call a power series, and instead of like previous sections, we were working with things that didn't have variables in them, right? So stuff like -1 to the n all over n factorial would be more akin to evaluating a function at one particular x value, right? So you're just putting x equals 1 basically into this formula for sine of x. Okay, so anyways, in this section, we're kind of making that connection between these functions that are kind of just thrown in your lap randomly, and the polynomials that we've grown to know and love over the years. Then in 9.8, we'll study without these weird functions. We'll just study these critters here, and we'll call these power series in the next section. And from there, in like 9.9, and this is where it gets kind of weird, we sort of back engineer these power series for functions. So we'll be able to find backdoor methods for creating power series to represent functions. And then finally in 9.10, we'll say without a doubt that we can say that these sequences of polynomials are converging to particular functions. Okay, and it turns out the way we learn how to build these polynomials in this section will be the way we, in general, will build these infinitely long polynomials to do the representation of the functions. Okay, so hopefully you'll hang in there through these last couple sections, and let's see how it goes. Okay, so first, we're going to look at just doing some approximations with polynomials. Okay, so basically, you're given some function like sine of x, and you want to build these things which you're hoping will converge to sine of x. You want to build a sequence of polynomials, right? So first, we have to learn how to build those polynomials. So building polynomial. And at this point, they'll just be approximations, polynomial approximations for functions f of x And we generally will kind of pin it at one point, like x equals c, and build around that point. So building polynomial approximations for functions, I should say around, not and, around some center x equals c. And usually the center will be 0. Okay, so anyways, what do we want to happen here? So let's pretend that we don't know what we're going after, but we're just kind of working this from the ground up. What do we want to happen? Well, clearly we want the functions to have the same value at the center. Okay, so we want our function that we're building these polynomials for to equal what the polynomials equal at the center. So the p thing here represents a polynomial. And usually we'll put like a sub index here, so p sub n, where n indicates the degree of the polynomial. So polynomial of degree n. We want these to equal each other, and what else would be nice? Well, the overall shape of the polynomial, we want that to be the same as the function. In order to get the shape correct, in other words, to try to get the polynomial to be going up when the function is going up, and to be curved concave down when the function is curved concave down. What do we need to happen for that? Well, we need the derivatives to be equal. So also then we would like the function and the derivatives to line up at this center C. So we would like f prime of C to equal p sub n prime of C, f double prime of C equals p sub n double prime of C, etc. And then all the way up to the nth derivative of C equaling the nth derivative of the polynomial at C. Okay. Okay, if this happens, then we get the polynomial to kind of be a really good picture for what the function is doing around some center. So anyways, we want to try this. We want to pick a function that's easy to work with, and usually they pick the exponential function because all of its derivatives are exactly the same. So let's explore the exponential function. So okay, so first we're going to approximate f of x equals e to the x with a first degree polynomial around the center c equals 0. Okay, so how do we do this again? Well, first off, what is a first degree? What does that thing look like? What does the first degree polynomial look like? We'll call it p sub 1 of x. And we're going to use the letters a for the coefficients. So usually you're used to saying first degree polynomial written as y equals mx plus b, right? We're going to write it in reverse order where the degree of the exponent goes up as you go to the right. So p sub 1 would be a sub 0 plus a sub 1x. A little different than what you're used to. Okay. So that's our first degree polynomial. Okay, so again, what do we need? We need the function and all of its derivatives to equal the polynomial and all of its derivatives. So we take a look at, here's f of x equals e to the x, and then we're going to need the first derivative, all the way up to the first derivative, that'll be e to the x. And then we need to evaluate these at the center, right? Because we need to basically build this kind of system of equations. So f of 0 will equal e to the 0, which of course is just 1. F prime of 0 will equal again e to the 0, which of course is just 1. And then we have to do the same thing for the polynomial. So p1 of x is a sub 0 plus a sub 1 of x. P1 prime of x. The derivative of a sub 0, it's a constant, so it'll just be 0. The derivative of a sub 1x will just be a sub 1. And then we evaluate these at the center. Okay. So p sub 1 of 0 will be a sub 0. P sub 1 prime of 0 will be just a sub 1. Okay, so what we want to do then is to equate these things to these things, and that'll allow us to solve for the coefficients of the polynomial, and then we could we'll have our polynomial, our first kind of polynomial in the sequence of polynomials. Okay, all right. So what's happening then? So first off, this guy and this guy. So set those two equal to each other, and what do we get? We get 1 equals a sub 0. Okay. And then set this guy equal to this guy. And what do we get there? We get 1 equals a sub 1. Okay, so pretty easy. Then we just substitute this material into this formula here, sort of our first polynomial approximation then, and our sequence of polynomials will be 1 plus 1 times x, so 1 plus x. Okay. If you were to look at the graph, this becomes a pretty good approximation, but only at that point, right? So here's e to the x. We're using this polynomial centered at this point 0, 1. And 1 over x has a slope of up 1 over 1, so it's basically going to y-intercepts at 1, so it'll look like this. And then if you zoomed in really close, like right here, you could see that it's pretty close to the original graph. It's just as you move farther and farther away from the center, it gets worse and worse. Okay, so what we're hoping is that the more derivatives you align, the better the shape will become, and that kind of gives you sort of an intuition about how the convergence is going to work. So if you have a sequence of these polynomials, you'll get there hopefully. Okay, so anyways, let's look at now. This is a first degree. Let's look at a second degree now. So our next example. Sort of approximating now with a second degree. So a quadratic, basically. So again, what does that thing look like? Well, p sub 2 of x will be a sub 0 plus a sub 1x plus a sub 2x squared. Okay. And then we go through the whole rigmarole again with, and I'm approximating f of x equals e to the x, just for things to be easy. So I need to go to the second derivative this time. And of course evaluate all of these at 0. And then I need to do the same thing with the polynomial. And hopefully if we do maybe one more approximation, a pattern is going to start developing. Okay. I'll evaluate these all at 0. Okay. So f of x is e to the x, and then so are its derivatives. Evaluating them at 0, you get 1, 1, 1. Here will be a sub 0 plus a sub 1x plus a sub 2x squared. Taking its derivative, you get a sub 1 plus 2 a sub 2x. Taking its derivative, you get 2 a sub 2. And then plugging 0 into each one of those, the first one you'll get a sub 0. The second one you'll get a sub 1. The third one you'll get 2 a sub 2. Okay. So for the first a sub 0 and a sub 1, again, we're equating to figure out basically this process will figure out the coefficients of your polynomial. Okay. We'll equate this to this, and then finally we'll equate this to this. Okay. So the first two are easy. A sub 0 is just 1. a sub 1 is just 1. But then a sub 2 is a little different, right? It's because you have 2a sub 2 equals 1. In other words, 2a sub 2 equal, or a sub 2 is what we're solving for, right? So a sub 2 divide both sides by 2. A sub 2 will be 1/2. Okay, so our polynomial this time, p sub 2 of x, will be 1 plus 1 times x plus 1/2 x squared. Okay. Okay, let's do one more, and then I'm going to kind of try to generalize this process so we can see maybe a pattern. And basically, it'll give us a general way of building these polynomials without having to go through at least half of the work. We won't have to do the polynomial part. We will still have to do this first part where you're taking derivatives of the function and evaluating them at 0. But the second half we can get rid of if we have a nice formula. So anyways, third degree approximation. So again, what does a third degree now look like? A cubic polynomial, p sub 3. It'll be a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed. The a sub 0, a sub 1, a sub 2, we already know what those are going to be. It's going to be 1, 1, 1/2. We're just going to need to figure out the a sub 3x cubed. Okay, so basically from the derivative stuff, we have all of that. We have kind of already all this information, right? All we need to kind of do is tack on f triple prime of x, which is e to the x, and then f triple prime of 0, which is equal to 1. So let me, if you allow me to, let me just do that. I don't want to have to rewrite everything. I'm not a big proponent of copying things down over and over. So here, let's see if we can get away with that. F triple prime is e to the x. F triple prime of 0 is going to be 1 again. And then for the polynomial part, you would have had plus ax to the third, and if you plug in 0, it's still going to be a sub 0. Okay, and then for the second derivative, you're going to have plus, and it's a sub 3 here, plus 3a sub 3 x squared. Okay, and when you plug in 0, you're still going to get a sub 1. And then for the last guy, this p sub 2 here, this will become 6, but I'm going to rewrite it as 3 factorial. Okay, instead, because 6 is 3 times 2 times 1, which is 3 factorial, and the factorials occur naturally in these patterns. Okay, so this will be 3 factorial a sub 3x. And then the last derivative, p sub 3 triple prime of x, will just be then 3 factorial a sub 3, and then p3 triple prime of x will just end up being, of course, then 3 factorial a sub 3. Okay, so to get so we know a sub 0 is 1, a sub 1 is 1, a sub 2 is 1/2, a sub 3 then is the troublemaker, right? So a sub 3 is going to be found by equating these two expressions. So we'll have basically, I'm going to have to rewrite that as 3 factorial a sub 3. So we'll have 3 factorial a sub 3 equals 1, and then you can solve for a sub 3 by dividing both sides by 3 factorial. Okay, so our p sub 3 polynomial is going to be 1 plus x squared all over 2, and we could rewrite 2 as 2 factorial. Okay, and then plus x cubed all over 3 factorial. And you kind of already see a pattern, right? So if you were going to do a sequence of polynomials here, like p1 would equal 1 plus x, p sub 2 would equal 1 plus x squared over 2 factorial. I think this is super obvious, right? 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And then p sub n, we can just speculate, right? It's going to be 1 plus x2 over 2 factorial plus x to the n all over n factorial. And then in The end chapter, chapter 9.10, will worry about taking the limit of the sequence of polynomials as n goes to infinity, right? So that will be the limit of the sum, in this case, of x to the n all over n factorial from n equals 0 to infinity. Well, not infinity, but some variable like, I don't know, we could do p, I guess. Whoops, too many p's. Let's do, I don't know, j. Oops, I'm still in erase mode. Sum n equals 0 to j as j goes to infinity. And we're hoping that that thing will converge, which is still an outstanding question, to the sine of x. Okay, so that's where we want to go in 9.10. We won't be able to get there until then. Right now, we're just solely focused kind of on building these polynomial things. And what this thing that we built, this piece of n thing that we've built here, this thing is called the nth degree Maclaurin polynomial. So it's a Maclaurin polynomial of degree n. And there's two types of polynomials, Maclaurin and Taylor's. Maclaurin just means it's centered at 0. Okay? If you have a Taylor polynomial, it's centered somewhere else. Okay? It's kind of silly. They shouldn't even bother differentiating the two, but they do. Okay? Anyways, so can we produce kind of a general mechanism or a general formula for producing these polynomials given a function? Okay, so the general formula for producing an nth degree Maclaurin polynomial. And yeah, we can kind of, we'll still need to be able to get these derivatives, but if you kind of scroll back and look at what we were doing, what were we doing? We were equating these coefficients kind of with the factorials attached to the derivatives of the functions evaluated at 0. Okay, so how did we build these coefficients? We noted above, in order to get the coefficients, we did the following. We equated f of 0 to the polynomial, the nth degree polynomial evaluated at 0. And if you think about what the nth degree polynomial looks like, let me just put that in parentheses right here, although it's kind of non-canonical here. P sub n of x would equal a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed, etc., all the way up to a sub n x to the n. If you put 0 into that equation, what are you going to get? You're just going to get a sub 0. Okay, so you're going to find that f of 0 will just equal a sub 0. And that would be basically your first term in your polynomial. It's f of 0. Okay? And then for f prime of 0, we equated that to the derivative of the nth degree polynomial. But if you take the derivative of this, the only thing that will survive once you take the derivative, so Pn prime of x, once you put in 0, it's just going to be, well, P prime of x will be a sub 1 plus 2 a sub 2x plus 3 a sub 3x squared. When you put in 0, the only thing that survives is just a sub 1. So this f prime of 0 will equal a sub 1. And then f double prime of 0 following the same, and we could kind of see what those terms are. These polynomials up here, when we were taking the derivative, were independent of whatever function we were using. It didn't really matter what function we were trying to approximate. So p double prime, where was that? It's right here. That's equal to 2a sub 2. So f double prime of 0 is equal to 2a sub 2. In other words, a sub 2 is equal to f double prime of 0 over 2. And then we figured out f triple prime of 0 was equal to 3 factorial a sub 3. So a sub 3 was equal to f triple prime of 0 over 3 factorial. And then hopefully you can kind of see the pattern, right? So I figure f4 of 0 will equal 4 factorial a sub 4. And so a sub 4 will equal f4 of 0 all over 4 factorial and so on. So in general, the coefficients are, drumroll please, a sub n equals the nth derivative of f evaluated at the center divided by n factorial. And that turns out to be true. So the Maclaurin polynomial is p sub n of x equals a sub 0 plus, and a sub 0, we want to write it in terms of the function, right, f of x. The Maclaurin polynomial for, so let's say that, so for f of x is, and we'll need f of x to have the first n derivatives. It'll be f, and you have to be able to evaluate it at the center. There's ways to get around it if you can't evaluate at the center. If you take, I think they're called Lorentz series, but we don't bother with that. That's like a complex variables type thing. But anyway, so just letting you know, even if it had an undefined point there, you could still manage to get around it. But for now, f of 0 plus f prime of 0 times x plus f double prime of 0 over 2. You can think of it as 2 factorial. You can think of this one as over 1 factorial and the first one over 0 factorial if you want the pattern. Oops, I forgot my variable. So that'd be times x squared plus f triple prime of 0 over 3 factorial times x cubed plus dot 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 plus fn, the nth derivative of f at 0 all over n factorial times x to the n. Okay, the Taylor polynomial then, the Taylor is just the same thing except with a different center. Okay, so the Maclaurin polynomial, the center is 0. The Taylor polynomial is centered at somewhere other than 0. So c not equal to 0, basically, polynomial. And it's basically the same deal, except instead of writing x, you write x minus c. Instead of writing 0, you write, so it's probably would have been easier just to say Taylor polynomial and then plug in 0. But we use the Maclaurin polynomial so much that they kind of, I guess that's probably the motivation. But anyways, for f of x is p sub n of x equals f of c plus f prime of c x minus c plus f double prime of c all over 2 factorial times x minus c squared plus f triple prime of c all over 3 factorial times x minus c cubed. And then, of course, all the way up to fn, the nth derivative of f evaluated at c all over n factorial times x minus c to the nth power. Okay? Okay. We're always going to have also these kind of summation notation versions, which I encourage you to use, but I'm going to leave it at this for now. Okay, so let's just work with finding an nth Taylor polynomial for sine of x, right? And I noted there at the beginning of our section, it's kind of one of our goals is to be able to produce these sequences of polynomials for these functions such that when you take the limit of those polynomials, you end up with a function. So we should be able to kind of build this thing now, at least the first part of it. And then in chapter 9.10, we'll look at the infinite version, basically, of the Maclaurin and Taylor polynomials. Okay, so the problem asks you to find the nth degree Maclaurin polynomial here. So when they ask for that, they mean the center is 0. And well, we're doing sine of x. Okay? So f of x is sine of x, and we want a 5th degree polynomial. Okay? So go up to x to the 5th is basically what n equals 5 means. Okay, so to do that, I can kind of dispense with the polynomial part because that's going to be the same for all functions, and we can then just worry about finding these f values, f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and for us we go all the way up to f to the 5th, the 5th derivative. So here we go. F of x, prime of x, f double prime of x, and then evaluate them on 0. Okay, so this would be sine, cosine, negative sine, negative cosine, sine, cosine. This will be 0, 1, 0, negative 1, 0, 1. Okay, and then we could just pretty much just copy and paste those values into our Maclaurin polynomial p sub 5. Okay, usually I kind of set it up like with some boxes, and you could do that on the test as well. So just plugging in the boxes. Okay, so what do we have? We're just copying and pasting this junk into those boxes. So 0, 1, 0, 0, 1, 0, negative 1, 0, 1. And then we can simplify it. Usually on a test, I'm okay if you just leave it like that. I'm happy with that for some students. That's good enough, especially if you're never going to take calculus again. It's good enough to just do that. But everybody else, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And that's like exactly the thing I was using way at the beginning of the lecture, right? So x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Yeah. It seems like it's a third, it should be p sub 3 because there's only 3 terms, but p sub 5 means the exponent is to the 5th power. Okay. Let's do a Taylor now. So find the nth Taylor polynomial. Okay. So this one has a different center. And here we go. F of x equals 2 over x. We want a 3rd degree and center it at 1. Okay, so here we go. F of x is 2 over x, which is 2x to the negative 1. And You're going to need f prime, f double prime, and f triple prime. And same for evaluating at the center. Okay, and then this will be -2, x to the -2. This will be +2 times 2, x to the -3. And then I like to not multiply everything out because it helps me see patterns and cancellations. Okay, that's a common technique amongst math people. So here, this next one will be -2 times 3 factorial x to the -4. Okay, so the f of 1, plugging 1 into x to the -1 is just going to be 1 over 1. So it's just 1. So you get 2. And the same for the rest of these. 1 to any power is 1, so you're just going to get 1 and when you put them into x. So this will be -2, you're just being left with the coefficients. Okay, and then we need to go to our third degree polynomial. So again, I like just putting stuff in the boxes. So this will be blank times x minus the center plus blank times x minus the center squared all over 2 factorial plus blank times x minus the center cubed all over 3 factorial. And then I'm putting in 2, -2, 2 times 2, -2 times 3 factorial. And you'll see there's a nice cancellation there. Okay, with the factorials. So this will be 2 minus 2 times x minus 1. 2 factorial is just 2. Okay, so those will cancel. You get plus 2 times x minus 1 squared. And then minus 3 factorials will cancel. You get 2 times x minus 1 cubed. Okay. Okay. So there's that. Okay, how good then are these approximations going to be? These polynomial approximations, and we're going to take a better look at that in the next section because we're going to start working with these things called power series, which are basically just these things, these polynomials, but infinitely long, right? The result of taking the limit of these polynomials as the number of terms goes to infinity. In that section, we'll talk about convergence of the x values and whether or not these things are even useful. Okay, so in some cases, they're not going to converge at all for particular x values. Okay, maybe they'll only converge at one place. So in that regards, there's kind of an issue there, whether or not they actually converge. The other issue is if they do converge, how good are these polynomial approximations as they get bigger and bigger? So it's similar to what we did with the alternating series estimation theorem back in the alternating series section. You're kind of bounding the error. Okay, so in the alternating series section, the actual difference between the sum and the nth partial sum was less than a sub n plus 1. We want to develop a kind of formula like that. This one will be a little more complicated though, okay? Okay, so anyways, how good basically are these polynomials? Do we really need to go out an infinite amount? Can we just use them as is kind of? Okay, how good are they? How many terms should we have if we want a good, to be within 0.0001? If we only have a 10th degree polynomial, is that going to be good enough for deducing trajectories of lunar modules, sending them to the moon and trying to land on a particular site, that sort of thing. So here we go. Okay, so approximations, and this is, I think the book calls it Taylor's theorem. Some books call it Taylor's inequality. So approximations I just call it Taylor's. So basically, there's going to be this R sub n of x formula, which you can think of as a difference between f of x and the nth polynomial, Taylor polynomial. Okay, So basically the error then is the absolute value of this, and the actual theorem is something like given a function with n+1 derivatives in some interval I, which contains the center, then for each x in this interval, there will exist a z value in between I and x such that, or in between x and c, sorry, between c and x, such that this r sub n of x is actually equal to the n+1 derivative evaluated at z divided by n+1 factorial times x minus c to the n+1, believe it or not. Okay. I think the book used to have a proof for this. They don't have it anymore. Usually in real analysis, if you take that class, they'll prove it. It seems like it has something to do with the mean value theorem. It's been like 10 years for me since I've taken that class. But yeah, in real analysis comes after advanced calculus. So you take advanced calculus in like your junior year, and then your senior year you take real analysis, and you would probably learn this sort of material. If you want a reference for that, if you're interested in the advanced calculus videos or something like that, you can always email me, and I'll send you a link to the video guide that I like. Yeah, so there it is. It looks like it's pretty nasty, and it's the way they derive it is actually pretty nasty as well. If you're not, already on a graduate level in mathematics, but you could kind of remember it fairly easily because it's kind of like the alternating series thing, right? You're basically, if you took the next term in line of our polynomial, that would be the n+1 of c all over n+1 factorial times x minus c to the n+1. So you see this next term in line is basically Taylor's theorem right there. So r sub n of x is less than or equal to that thing, kind of. Okay? Except instead of c, you have this general z term. Okay, so I mean, intuitively, that gives you a way of kind of remembering it. I doubt that's exactly how they prove it. I know that's not how they prove it, because I thought maybe that's how they proved it, and then when I went through real analysis, no, that's kind of not it. But yeah, so there it is. In general, when we use it, we use the inequality. So in general, what we'll have to do when we're trying to work with these approximations, we find the maximum of this n+1 derivative on this interval from I to z. And it's not just the maximum of that, it's the absolute value of this thing that we're wishing to maximize. So in general, we find the maximum of this object on the interval from x to c. It could be c to x or x to c. And then consider the inequality which they call Taylor's inequality, R sub n of x, absolute value of, is less than or equal to the maximum of this absolute value of the n plus first derivative of x on the interval from x to c, all over n plus 1 factorial times the absolute value of x minus c to the n plus first power. Okay. And on a test, I won't have you do any of these approximations. These tend to be a little more intensive, so I'll leave it to the homework to try to teach you this. But I mean, I'm going to go through the examples, the idea. Okay, so using this formula, there's two versions of the problem. Given a Maclaurin or Taylor polynomial of degree n, how good is the approximation? And then the other version of the problem, given some sort of error tolerance, how many terms of the polynomial do I need in order to make sure it's within this error? Okay, so let's look at the first type of problem where we're just trying to determine how good the nth degree polynomial approximation really is. Okay, so in this example, we want to use the Taylor's theorem, I guess Taylor's theorem, or Taylor's inequality, to approximate sine of 0.1 with the third degree polynomial p sub 3, and they want you to determine the accuracy. Okay. So first off, just noting the third degree polynomial for sine x, which I found already up here. Oh wait, that's ln x. This is the fifth degree, so all I need is the third degree, so I just need these two terms for sine x. Okay. So note first, what is p sub 3 of x? That's just going to be x minus x cubed all over 3 factorial. Next, we consider the R sub n formula in this context. Absolute value of R sub n of x, the x value. So we kind of go through, we can input information, right? We know the n as well. To the side, there's 4 things you kind of need for this inequality. You need the n value, sort of. You don't always need it, but you need to have just one unknown to kind of pull it off. You need the x value, you need the c value, and we have all that, right? This is a Maclaurin. They say it in the book. I probably forgot to read it. It's to approximate sine x with p sub 3 of x, which is Maclaurin. In other words, the center is at 0. So c is 0, x is 0.1, n is 3. We also need to know the max of the n plus first derivative of x on the interval from x to c. So in this case, it's c to x. Okay. So we have this kind of one unknown we got to worry about. But anyways, let's try to fill in the blanks here, right? So it's usually r sub n, so r sub 3 of x, x is 0.1, and then that's less than or equal to this thing we don't know, the max of the absolute value of the n plus first derivative of x. That's all over, yeah, so n, again, I could put that in there. So n is 3, so this would be the fourth derivative, all over 3 plus 1 factorial, which is 4 factorial, times the absolute value of x minus c to the 4th power. Okay, so that's equaling the max, the absolute value of the 4th derivative of x, all over 4 factorial, times the absolute value of 0.1 is just 0.1 to the 4th. Okay. So we need, in particular, to figure out this thing. What is that thing? Okay. So we need to figure out the max of the 4th derivative of x. Okay. So note, you can literally find it, right? So fourth derivative isn't that bad. F of x is the sine function. F prime of x is cosine. F double prime of x is negative sine. F triple prime of x is negative cosine. And then finally f4 of x, we get back to sine of x. Okay. So the absolute value of sine of x, oh, we want n plus, no, that is n plus 1. Okay, so the absolute value then of that thing is what we're trying to maximize. The absolute value of sine of x is always going to be less than or equal to 1. And that just comes from the fact that sine of x itself is in between 1 and negative 1. And all we're looking for is an upper bound. Okay, so it has a lower bound of 0. But for this work, we just need the maximum, right? So 0 would be the minimum. We're looking for the maximum, which is 1. So we'll be able to say then the max of the fourth derivative on this interval from 0 to 0.1. We can do better than what we have, but without a calculator and stuff, we're kind of just going to let this be 1. Notice in general, for these type of cosine or sine approximations, the n plus first derivative, the absolute value of that, is always going to be either sine of x or cosine x. And both sine of x or cosine x are going to be less than or equal to 1. So in general, you can always do this if you're working with your f of x being equal sine or cosine. Okay, so anyways, going then back to our r sub n formula, we have then r sub 4 of 0.1. So we have r sub 4 of 0.1 is less than or equal to this max thing, which we're replacing with a 1, all over 4 factorial times 0.1 to the 4. Okay, and that gives us our kind of error in this fourth degree polynomial, which you'll see is relatively small. It's 0.1 to the fourth divided by 4 times 3 is 12 times 2 is 24. So it's really small, 0.1, 2, 3, 4, 5, 5 zeros in there. Okay, so the accuracy, pretty close to the actual value that you'll see in your calculator. We can determine then an approximation for sine of 0.1 using p sub 3 of 0.1. Okay, so if we kind of go back and consider what is p sub 3 of 0.1, so right here, p sub 3 of 0.1, that's going to be 0.1 minus 0.1 cubed all over 3 factorial. Okay, so that'll equal 1 minus 0.1 cubed divided by 3 times 2 is 6. So that's what, 0.099833-ish. So we have the difference between f of 0.1 and p sub 3 of 0.1 being in between, this 0.1 to the fourth all over 4 factorial. So less than or equal to that. And then you can just add p sub 3 of 0.1 to both sides, and you'll note that sine of 0.1 will be in between those two values. Okay, so basically 0.09983 minus the 0.1 to the fourth over 4 factorial, which was 0.235. On this side, you'll have 0.09983 plus 0.12345. So f of 0.1 will be in between 0.099837 and 0.099829. Okay. Okay. So that's the first type of problem you'll see. The second type of problem then will be how many terms of the polynomial do I need to pull off my approximation, right? Okay, so let's look at another example then. Determine the degree of the polynomial needed to approximate ln of 1.2 to be less than this error of 0.001. Okay, and in this case, they want you to center the polynomial at 1. Okay, so first we have to build this polynomial. Then we have to work with that Taylor's inequality. And then kind of what will end up happening is this R of n expression, we won't know n. Okay, we'll be able to find x and c in the maximum, but we won't know n. And we'll use the inequality to solve for n. Okay. Okay, so let's take a look at this guy then. I need to build the polynomial. So f of x equals the ln of x. And I don't know the degree, so this makes it even harder because I kind of have to find the nth derivative, find a pattern, and then construct an nth derivative. Then I need to evaluate all of them at that nth derivative. But anyways, I'm going to need the n plus first derivative eventually, right? Because in the remainder formula, I need that n plus first thingamajig, so I'll have to get that as well. So I'm going to try to kill two birds with one stone here for the sake of time and sanity. So f prime of x is 1 over x, which is x to the negative 1. F double prime of x is going to be negative x to the negative 2. F triple prime of x is going to be 2x to the negative 3. F to the fourth of x, the fourth derivative will be negative, and I'm going to use factorial notation, so negative 4. Fifth derivative goes positive now, 4 factorial x to the negative 5, and I think that's good enough for me to see a pattern. So I need this formula for the nth derivative in order to build my polynomial. So let's look at that. I don't even know if I really need to build the polynomial. I mean, they're not asking for it, right? They just need the degree. They don't really need me to build the polynomial. Yeah, I don't think we need that. But anyways, let's get the nth derivative here. So this will be negative 1 to, let's see, the even guys are negative, so I need n plus 1. And then we have something factorial, and it looks like it's, you know, if it's the third derivative, it's 2 factorial, fourth derivative, 3 factorial, fifth derivative, 4 factorial, nth derivative, n minus first factorial, and then x to the negative, third derivative, negative 3, fourth derivative, negative 4, fifth derivative, negative 5, nth derivative, negative n. Okay. And then I'll need the n plus first derivative. And what will that be? That will be, so the only part that you worry about is, it looks like there's a lot of variables, but really the only variable is x. This is, all that red stuff is just a coefficient. So when you take the derivative, that kind of stuff just stays the same. Negative 1 to the n plus 1 times this n minus 1 factorial. You bring down the negative n, and then you have x to the negative n minus 1. Okay. You can rewrite this to make it look a lot prettier. So this will equal negative 1 to the n plus 1 times n minus 1 factorial times negative n is the same as negative 1 times n. And then we have x to the negative n minus 1. you can combine this and this by adding the exponents, right? Because -1 is really to the first power. So -1 to the n plus 1 then will be -1. So I'm doing this kind of in my head. Let me write out what I'm saying. So -1 to the n plus 1 times -1 to the 1 will be -1 to the n plus 2. That will equal -1 to the n times -1 to the 2. -1 squared is just +1, so you end up with -1 to the n. Okay, so this will be -1 to the n. And then we have n times n minus 1 factorial. Well, that's just n times n minus 1 times n minus 2 times n minus 3. That's just n factorial, right? Because we recall our recursive definition, n is equal to n times n factorial, is equal to n times n minus 1 factorial. Okay, so n times n minus 1 factorial must be equal to n factorial, just a commutative law of multiplication. So we get n, let me write that back in white, n factorial times x to the negative n minus 1. And then for our R of n formula, we need the maximum of the absolute value of that thing. Okay, so right now we have f to the n plus 1 for, let's remind ourselves, for our inequality thing, we need the max of the n plus first derivative of x, the absolute value of that, on the interval that we're worried about. So the interval we worry about is from x to c. C is 1, x is 1.2. So the max on the interval from 1 to 1 point whatever, all over n plus 1 factorial times x minus c to the n plus 1. So we're looking for this thing. Okay. Originally I thought maybe I had to build the polynomial, but I'm not going to, okay, because we really don't even need that. So anyways, what is then the absolute value of this thing? So let's get that going. The absolute value of the nth derivative of x, the n plus first derivative, n plus first derivative, the absolute value will get rid of that -1 to the n thing. So you just end up with the absolute value of n factorial times x to the negative n minus 1. Okay. On our interval, we want to maximize this on our intervals, right? So the interval is from x to c. X is 1.2, c is 1. So we're going from 1 to 1.2. We want the max of this thing. The absolute value of that thing on that interval, the x will be positive no matter what, right? So because we're going from 1 to 1.2. So this thing we're looking for is basically the max of n factorial times x to the negative n minus 1. We don't need to worry about the absolute values. Okay, so here we go. How the heck do I maximize this thing, right? Well, Calc 1 says you take its derivative, find the critical numbers, all that jazz. So that's what we do here. Let's call this something else. Let's call it g of x. So g prime of x will equal the derivative of this thing, okay? Well, no, we don't want to call the max that max thing. It's this thing we want to call g of x. Okay? We want to take the derivative of that to maximize it. So that then, the coefficient is not n factorial, and then the derivative of x to the negative n minus 1, you bring down the negative n minus 1, and then you have x to the negative n minus 1, which would be minus 2. Okay, and we could rewrite that as negative times n plus 1 times n factorial all over x to the n plus 2, which will equal negative n plus 1 factorial all over x to the n plus 2. Okay. This derivative for all values in that interval is going to be negative. In other words, it's less than 0. In other words, it's decreasing in that interval. Hence, the n plus first, this absolute value of the n plus first derivative of f is decreasing. So what? Well, that means it looks like this over the interval. It's like this. So where is, well, that's not really decreasing, is it? Let's make it clear. So that function looks like this. So where is its maximum? Its max is going to be right here on the left-hand side of the interval. Okay. So hence, its max is at 1. Okay. Hence, the max of the absolute value of the n plus first derivative of x over the interval from 1 to 1.2 is going to equal this thing evaluated at 1, the absolute value of n plus 1 of 1. So let's go upstairs and look at what that thing was. It's this thing. If you plug 1 into that, you just get n factorial. Okay, so now finally we can go back to our remainder function. So here's our r sub whatever of x. Let's see what information we have. We know x is 1.2, c is 1, n is unknown, and then the max thingamajig we found to be n factorial. Okay, so r sub n, we don't know n. X is 1.2. This will be less than or equal to the max of that thing, n factorial, all over. It's always then n plus 1 factorial times the absolute value of x, which is 1.2, minus c, which is 1, raised to the n plus first power. Simplifying then, n plus 1 factorial is the same as n plus 1 times n factorial, times the absolute value of 1.1 minus 2, or sorry, 1.2 minus 1 is 0.2, raised to the n plus 1. And you can remove the n factorials, so this is equaling 0.2 to the n plus 1 all over n plus 2. Okay, we want that thing to be less than 0.0001. Okay, that's given in the problem. Okay, you're not going to be able to solve that inequality, so you have to do trial and error. Okay, so by trial and error, we notice the following then. So start with n equals 1, and an nth degree polynomial. So we have 0.2 to the 2 power all over 3. Okay, so what is that? 0.2 to the second power divided by 3 is 0.013 repeating. That's not good enough, right? So you try n equals 2. So you get 0.2 cubed all over 4. That'll be 0.002, close, but not close enough. So try n as 3. You get 0.2 to the 4th all over 5. And that one does the job. So 0.00032, which is definitely less than 0.001. So hence, we need a third degree polynomial approximation. So hence, you need p sub 3 of x, and we can even find that using our work from above. Let me see if I have it written somewhere. Probably not, right? Ooh, I guess I didn't write it anywhere. We can go back up here and kind of figure it out, right? So f of 1 is 0, f prime of 1 is 1, f double prime of 1 is negative 1, f triple prime of 1 is 2. 1, negative 1, 2. So what do we have? P sub 3 of x is going to be 1. That'll only get us up to the second polynomial. So 1, negative 1, 2. 4 of 1 is negative 3 factorial. Okay, so basically just plugging in the boxes again. Plus blank x minus 1 plus blank x minus 1 squared over 2 factorial plus blank x minus 1 cubed over 3 factorial. Plop in the numbers, 1, negative 1. Oh, whoops, the first one was 0, wasn't it? So maybe I did have enough. Oh, frick. I erased the wrong one. Sorry. Plus blank times x minus 1 cubed over 3 factorial. First one was 0, right? Yeah. Okay, so I screwed that up. So it's 0, 1, negative 1, 2. So it's be x minus 1 minus x minus 1 squared over 2 factorial plus 2. And of course there's some nice cancellations, so this will just be 3. So you can even get rid of that, make it look a little prettier. X minus 1 cubed over 3. And then you can guess the next one's probably minus x minus 1 to the 4th over 4, etc. Okay, so there it is in all its glory. Okay, good enough. We'll see you next time. Thank you for watching.